Hello, everyone. Welcome to pre-lecture 3. This lecture is going to cover some of the properties of liquids that come out of understanding their intermolecular forces. Let me also say that all of the material in this video will not be on quiz 1, but it is fair game for quiz number 2. Okay, so again, all of the material in this video, fair game for quiz number 2, but it will not be on quiz number 1. Okay, so once we know and can kind of conceptualize what the intermolecular forces are that are present in a molecule, a lot of those intermolecular forces, as well as some other properties such as the shape or temperature of a system, will determine some of its physical properties. And so some of the ones that we're going to touch on today are viscosity, surface tension, adhesive and cohesive forces, as well as capillary action. And so starting with viscosity, this is a property that you're probably familiar with, and how we define it, it is the measure of resistance to flow in a liquid. And so liquids such as water, gasoline, others that we would consider to have free flow are low viscosity liquids, whereas more viscous or high viscosity liquids such as honey, syrup, motor oil, anything along those lines, we would say have high viscosity. Okay. What ultimately causes high viscosity is generally larger or more structurally complex molecules, or I should say, stronger intermolecular forces between the molecules. So that it is more difficult for them to move past each other, and thus creating a greater viscosity in the liquid. Okay. If we think about viscosity in relation to temperature, a reminder that temperature is essentially just a measure of our kinetic energy. So as the temperature increases, the kinetic energy of our system also increases, which will make something less viscous. Okay. So here's a quick exercise for you. So I have a table of chemicals here and their chemical formulas. And I want you to pause the video and think for a sec what intermolecular force is going to dominate each of these molecules. And so if you want to do that, I'm going to continue on now. So with water, of course, hydrogen bonding is its most dominant intermolecular force. Mercury is a pure element, so it just has dispersion forces. Ethanol, we talked about in class last time, has a hydrogen bond. Octane is entirely nonpolar bonds. So a reminder that when we have just carbon and hydrogen, everything will be nonpolar. That means it's dominated by dispersion forces. Then we have ethylene glycol, which also has hydrogen bonding groups. And so you can see that the intermolecular force that is present, so for example, dispersion forces are weakest intermolecular force, but because mercury is so heavy, it's got such a large size, it still has a higher viscosity than something like water that has a strong intermolecular force in hydrogen bonds, but a low molecular weight. And so if we're talking about physical properties, really we're oftentimes balancing the strongest intermolecular force as well as the size of the molecule. And some of these physical properties, in fact, are how we understand those. Okay. So that was viscosity. Moving on to surface tension. Surface tension is defined as the energy required to increase the surface area of a liquid. Also could be defined as the force required to increase the length of a liquid surface by a given amount. And so, for example, we have some beaded water here on a spider web. And essentially, anytime you see that kind of curvature in a liquid, that is indicative of surface tension, where the surface of our liquid is going to be stretching. Okay. It ultimately results from cohesive forces between molecules. So that is to say, in our example here, our water molecules are sticking together because of their intermolecular forces. And it causes the surface of that liquid to then behave like a stretched rubber membrane. Okay. Among common liquids, some have distinctly high surface tensions. Essentially, the greater the intermolecular force, the greater the surface tension. So Water has greater intermolecular forces. This is another place where we balance intermolecular forces with molecular weight. So mercury, again, strongest intermolecular force is dispersion forces, but because it has such a high molecular weight, it actually has a very high surface tension. Would highly recommend clicking on this link at some point. You can see a really cool video of another metal, gallium, having very high surface tension, as well as our other molecules here. When we get something like ethylene glycol, where we have decently high molecular weight, as well as hydrogen bonding capabilities, we end up with a very high surface tension as well, or at least a pretty high one. Okay. So this surface tension represents a kind of tough skin that essentially creates that beading that we see in something like water on a windshield or a spider web before it will break. Okay. Next up, we have adhesive and cohesive forces. And so something that is adhesive is when we have an intermolecular force that is attraction between two different types of molecules. So for example, we have water and then we have a surface of glass here. And so when we get that kind of concave meniscus in our water, anytime we put it in glass, that's because there are adhesive forces between water and glass that actually pull the water kind of up the sides there. And so we have water in contact with that surface. We can also have adhesive forces where the molecules, or cohesive forces rather, where the surface of the liquid is relatively weak, but it essentially disperses out from there and does not wet the surfaces because it would rather cohere than adhere, if that makes any sort of sense. Okay. So keeping with water as kind of a classic example, water will form droplets on surfaces where there are cohesive forces, where the water will hold to itself, and those cohesive forces will be greater than the adhesive forces. And then water will wet a surface. So something like concrete would be where water, instead of forming like beads of water, like on the windshield or a spider web, the water would spread out on the concrete and wet the surface because the adhesive forces there are going to be greater than cohesive ones. Okay. And I believe the last one we'll talk about today, capillary action. This is when a liquid flows within a porous material. So the example here is this line that you can see if a paper towel were stuck into the line perpendicular to it, the wine would start to move up. And that is because the molecules, the water, the ethanol within, as well as all the red parts, of course, within our wine will actually be attracted through adhesive forces to the makeup of the paper towel. So that would be these molecules here. And that actually pulls the liquid up a certain amount of way. And so that is something called capillary action. Okay. All right, so shifting gears a little bit, those were some of the physical properties of liquids. I also want to talk about phase transitions. And so we'll get a lot more into this in class, but I wanted to at least preview it here, where of course we have our three main phases of matter: gases, solids, and liquids, and we can go between them. And so ones that you're probably familiar with are evaporation and condensation when we go between a gas and a liquid. If we go between a solid and a liquid, we have melting and freezing. And then the one that's, or the two that are probably new to you, if we go from a solid to a gas, that's a process called sublimation. If we go from a gas to a solid, that is a process called deposition. Okay. So these are the various transitions, and we're gonna talk more about them in class, or which it says today, but depending on when you watch this video, we will talk about them in class. Okay. So starting to preview those, let's talk about vaporization and condensation. This relates to the movement between gas and liquid state. And so when we have a rate of condensation that is equal to a rate of vaporization, that is to say, Our gas is forming at the same rate the gas is also condensing into a liquid. When those two rates are equal to each other, there's in a sealed container, I should say. So you'll notice that this container in this example is sealed. Then things are said to be in a dynamic equilibrium, meaning that gas and liquid are still interchanging, but because they're doing so at the same rate, that is then equal. And so when they are equal, that means that the process is still occurring just at the same rate. And this actually creates another property that we can measure, and it's called vapor pressure. So this is the pressure of the gas that is exerted in a closed container when the system is in dynamic equilibrium between a liquid and a vapor. So you'll notice here, basically we get a movement, and the difference, how much gas fills up the chamber, will ultimately result in a measurement of pressure. Okay. So molecules with strong intermolecular forces will impede vaporization. So things will oftentimes stay liquids when they have stronger intermolecular forces. That means they will also favor, quote unquote, recapture of gas phase molecules. And so those sorts of molecules will have relatively low vapor pressures, whereas molecules with low intermolecular forces tend to have pretty high vapor pressures. Okay. We can also think about vapor pressure, or vaporization at least, in terms of temperature. So if we increase the temperature of our system, a reminder that the average kinetic energy will go up. And as the average kinetic energy goes up, we will also then have a larger proportion of our molecules enter the gas phase relative to the liquid one. And so the example here, the black line, we have a higher temperature, we have less molecules at kind of our peak, but we have a higher number here that cross this line of having the minimum kinetic energy needed to escape the liquid and turn into a gas. And so all this to say, when we warm something up, it is more likely to be a gas than a liquid, right? That'll be the end of our pre-lecture for today. If you have any questions, feel free to let me know. Also, I will state again, none of this material will be on quiz 1. And so if you have any questions, email me. Otherwise, you can ask them in class. Have a good day, and I will see you soon.